that we took a makeup class on this Wednesday, and we discussed about, I think, velocity triangles and relative and absolute motion, and then for one-dimensional case, when there is no angle involved, so it means that we can find the relative velocity as well as the absolute fluid velocity by considering the object speed. So, in case of turbo machines, that object is basically the rotor blade speed. So, in those cases, we need to kind of draw the velocity triangle depending upon the position, whether that is inlet to rotor blade or outlet to rotor blade, and we discussed those things in detail. Now we are going to officially say or formally start the turbo machines chapter. So, is there any query from the last class which we had on Wednesday? You can ask me now, otherwise we can start the turbo machinery chapter, which is basically the last chapter for this course. So it seems that everyone is happy with the understanding level we developed for the velocity triangle. So now we will start with the basic introduction of turbo machines. Okay, so turbo machines, or we also call them like they are one of the type of fluid machines. So fluid machines are the machines which depend upon the interaction of fluid with that particular machine. So it can be pump, it can be turbine, and so turbo machine is one type of fluid machines. So first of all, what are the yes anything? Okay. So what are the application area of turbo machines? It involves anything where we have got a rotor like wind turbine, like compressor, like hydraulic turbine, then water flow rate measurement meter, then fan, ceiling fan, and blower, then what else? Pump. So anything which has got a rotor in which there is some kind of rotor blade, so that either we can impart the momentum to angular momentum to the fluid, or we extract the angular momentum from the fluid, which is the case of turbine. And if we are giving the angular momentum to the fluid, then that is the case of pump or compressor, so or ceiling fan for that case. So this is the slide where we see that there are many applications of turbo machine. Like it is here that we have got the kind of this we call it here we have got turbine and as well as nozzle installed. So we can get the speed of the we have got two engines. So in engine we have got compressor as well as a mini turbine inside this, and then wind turbine, and then compressor blade, and then the water flow rate measurement meter. So generally speaking, turbo machines are everywhere in engineering applications. Now, as I mentioned that fluid machines have got two types. So at the start, I discussed that what are fluid machines? Fluid machines. Those are the machines in which the fluid interacts with that machine, and either the fluid gets the energy from the machine, or it kind of gives the energy to the machine. So if it is getting the energy from the machine, then it is that kind of arrangement is called pump. And if the fluid is imparting energy on that machine so that we can convert it into electrical energy, then that machine would be turbine. Now it has got two types. One is positive displacement machine. So in positive displacement machine, the fluid is forced into or out of a chamber or control volume. We can call it by changing the volume of chamber. So it means that we don't have any rotary motion in that. So it is just the fluid is either coming in or going out of that control volume by changing the volume of chamber. The very common example of that is human heart. So it's kind of pump the blood out to every part of the body and then take it back. And then the other one is if you have ever experience of riding a bicycle, so there is a bicycle pump. So it's kind of the when we push that plunger down, then it is kind of we are forcing the compressed air into the tire of bicycle. And then what else? Maybe is the engine of car. We have got reciprocating motion, that piston cylinder motion. So those are the examples of positive displacement machine. So and then second type of fluid machines are, we call them turbo machines. So turbo machines are the machines in which energy is transferred or extracted from to the fluid by a rotating component which is usually installed on a shaft, right? And when that energy is being transferred, then the momentum, angular momentum, and pressure of the fluid changes. It increases in case of pump and it decreases in case of turbine, right? So the example of that, if you have got a desktop in your home, then there is a fan installed there to cool the electronic components. So it's kind of a fan. It is a rotary motion. Then we have got ceiling fans, and then in case of steam power cycle, we use pumps in homes. We also use pumps, and then we have got turbines, hydraulic turbines like Celsius turbine, Kepler turbine. So those are the examples of turbo machines. So in this course, we are going to discuss turbo machines in detail. So just to show you the figures of some of the examples of these fluid machines, one is tire pump, human heart, and then reciprocating pump. And then we have got turbo machines. So in that we have got a rotor and we have got a dynamic motion or rotary motion of that rotor. And turbo machines involve the collection of blades, buckets. Buckets mean casing, flow channels, or passages arranged around an axis of rotation to form a rotor. So this rotor can have a casing as in case of the centrifugal pumps, we call it scroll, or it can be open like ceiling fan. So there is no casing of ceiling fan. So it is kind of open flow outside that fan, right? So now, if we talk about the turbo machine, we have in terms of work done types. If we turbo machines types, if we say that, then we have got. We all know that there are two types. One is pumps. It adds energy to the fluid. So it means that if the flow which is coming into pump, so here we have got pump, then we kind of uh, get energy inside this by some motor. So then, if this is energy in of the fluid and this is energy out, then energy out would be greater than energy in case of pump. Right? Work is done on the fluid to increase its pressure, and then that pressure can be used to move the fluid from one place to another, like in case of the centrifugal pump installed at our homes. That pressure is used to move the fluid against the gravity, so that the fluid can be transported from the ground level to the overhead storage tank, which is there at the rooftop. So that is one purpose of pump. So now, what are the practical examples of pumps? They are like centrifugal pumps and axial pumps. Then we have got fans, blowers, and compressors. Now, so it means that in pump is just a generic word to say that in this kind of turbo machine we are adding energy, but we also use pump as a practical application. So like I told you that there are like certain things: fans, blowers, pumps, and compressors. What are the difference between these two? Between these three? In fans, the pressure rises minimal, but we are more concerned about high volume flow rate, right? And then what about the blower? Like the dryer we use at home to to dry our hairs. So that is so pressure. In this case, the pressure rise is intermediate, and volume flow rate is quite significant. Okay, and then we have got like I talked about dryer, and uh, the blower installed in the cars to for the blowing of air through the vents for AC. So that is also an example of that blower, and then pump. What is pump? That here the pressure rise is high pressure difference. High pressure difference for liquid. So it only increases the pressure of liquid pumps. And for the compressor, it is for the high pressure application for the gases. Like we install compressor in turbojet or maybe in our air conditioner where we have to compress the vapor refrigerant. So that is the compressor. Let me write it here. So and for the pump we are talking about liquids. So it is just to increase the pressure of liquid, and for the compressor it is used to increase the pressure of gases, any fluid which is in gas form. Whether that is air or whether that is refrigerant, it depends on the particular application. Right. So these are the four types of pumps, and then the second type of turbo machinery. When we talk about the nature of work, that is turbines. So in turbines, energy is extracted from the fluid, and in the process the fluid pressure decreases. So we can say that if we have got a turbine here, so it means that the flow is expanded in this case. So it means that when pressure is decreased from input to output, so it means that the fluid would be expanded. So we usually call it a expansion process in steam power cycle. So energy in and energy out is defined. So here we get net work output, uh, which is on a rotating shaft. So and then this shaft is attached to some generator to produce electricity. So here we can say E of out is greater than E of in. So that it means that whatever energy fluid imparts on the turbine blades, that would result in decrease in its energy at the outlet, right? So what are the examples of these? Like wind turbine, steam turbine, gas turbine. There are many types of turbine which are used in industry. And if you remember in the previous class, we also kind of used that sprinkler or water fountain to work as a turbine, and we determined it, calculated the power output of that and torque and everything. So I hope that you can kind of see its application. Right. So now, if we say that how does a turbo machine looks like, so let me show it on the different parts of that. So we discussed about these pumps, different types of pumps, fans, blowers, pumps, compressors, and then turbines. Now, when we say that what are the different parts of a turbo machine. So let's take an example of a turbine. So here we have got an axial turbine. You can see some casing and then some black portion on which the that shaft is attached, on which the air we have got stator blades which are shown here, and then after in stator blade in the axial direction we have got rotor blades. So let me show you that in the parts. So if I can make it a little bit more visible to you, maybe it would be helpful for all. Okay. So now here, if you can see that we have got these are the blades which are attached to the casing. So they are called stators. stator blades, and then if we pass the stator blade towards from left to right like this, then we would have a stage of rotor blades. So that is shown here. This is the casing, which is stator, and then we have got, these are the rotor blades. So stator blades are there just to guide the fluid so that they can strike the rotor blades in at an optimum angle, so that the torque which is produced by the rotor, that is maximum, because the stator blades, they are attached to the casing, so they are not going to move, they are just there to guide the fluid. But these rotor blades, they are attached to the rotating shaft, and then when the fluid passes through the stator blade and then strikes the rotor blade, it changes direction, and as well as the pressure, depending upon the angle of that strike with the collision with the rotor blade, it also imparts some rotational energy on this blade. So as the consequence, this shaft would rotate because of the torque which is being applied on the rotor blade, and then afterwards we would have some kind of generator here, so that would produce electricity, right? So that is kind of the different parts of generic axial turbine. So now we can show it in the same thing in a two-dimensional view. Let me first of all, if I can. Okay. So, now, if we can show that here the fluid flows directly into the device in an axial direction, so it means that the arrows which are shown on the left, which are the red arrows, so the fluid is going in the axial direction, right? And then the stator blades turns the flow so that it is lined up with the rotor blade. So here I have shown the kind of, this figure is shown from the front, right? So from this side, if you look from this side, here the first row, if you see that aerofoil like cross section of the blade, so what happens that this is the axial direction. Now the shaft is attached here, which is being rotated. So first the fluid comes here, and the stator blade, which is the first row, it changes its direction so that it can strike the rotor blades in an optimum direction. So when it strikes the rotor blade here, it changes the direction. So because of change in direction, rate of change of momentum occurs, and rate of change of momentum is equal to the net force which is going to act in this direction from right to left. So it means that it would have kind of anti-clockwise rotation if we see it from the front. It means that the shaft would rotate, and in front of shaft we would have generator, right? So I hope that a general principle of functionality of a turbine it is clear to you. So we are talking here about the radial, about the axial turbine only, not about the radial turbine. They are also a kind of turbine which we discussed in the last class when we discussed about the centrifugal pump. So if we want to classify turbo machines in terms of nature of flow paths which the flow takes, so one is axial flow turbo machines. It means that the path of the general path of the flow is entirely or approximately, it is parallel to the axis of rotation. So it is an example of the fan which is installed in your workstations at home. So what happens that it kind of takes air from one side and it throws that air on the ICs installed in that your CPU, So it is also installed in the laptops as well, right? So in these kind of machines, turbo machines, the direction of flow is parallel to the axis of rotation, right? So it means that the flow comes from here and then it travels kind of in the axial direction along the rotating shaft, right? One example of axial flow turbo machines is Kepler turbine, or as well as the fan which is installed in our in our laptop, right? And then another example is that the fan which is installed in front of radiators in cars. So that is also a kind of axial flow fan, right? Or turbo machine, right? And then the other type of turbo machine with respect to the flow path, that is radial flow turbo machine. So radial flow turbo machine, in that the flow comes in the axial direction. Like here the flow would come from from into the board towards the out of the board, and then at impeller we call it impeller, from where the from impeller eye, it means that it is coming from that impeller eye, the fluid is coming from there, and then due to the arrangement of blades in the radial direction, it goes out in the radial direction like this. And like the flow comes in the axial direction out of the board, and then it moves from here to the in the radial direction. So they are centrifugal pumps which are usually installed in our homes. Let me show you the example in a better way, maybe here. We discussed that somewhere here. Yes, you should see here that this is the impeller eye. So here the fluid is coming in the exact direction out of the screen, and then when it comes out, there are the impeller blades. So the here the flow direction is predominantly in the radial direction, and which is also shown on the side view. So it is coming in the x direction, and then it is going in the radial direction, which is also shown on the front view as well. So this is the, and as well as the title is also the radial flow devices. So you can see that it is type of radial flow turbo machine. So all these slides are, I have taken it from different sources, so don't expect to find all these slides in the book. So just to, like these slides, I have taken it from another resource. Maybe I would share that introductory book about the turbo machine. It is kind of 50 pages book. It is very readable for a beginner who wants to learn about something about turbo machines, and it is very simple in terms of the understanding. So maybe I would share that book as well for the convenience of your understanding. So because you are not going to find these things in the textbook which I have shared. Okay, so we were here at this point. Okay, so we talked about axial flow turbo machines, radial flow turbo machines, and then we have got another one which is kind of mixed flow turbo machines. So in that the flow is partially radial and partially axial. So we call it mixed flow turbo machine, and Francis turbine, that is one of the prime example of mixed flow turbines. So we would discuss it when we will discuss a Francis turbine. So in detail, so you would understand that. So, and these are the three types of turbo machines as per the nature of flow path or direction of flow path, we can call it. So from here now we would start discussing pumps. We would start discussing pumps, and then we would move on to turbines after that. So, let me. So, whenever we analyze or do any calculation of pumps, we need to know certain parameters regarding the specification of pumps. So, the first parameter which comes to our mind, that is the volume flow rate. So, if you go into the market to find the any pump, you have to specify the volume flow rate. It is usually specified in volume flow rate and brake horsepower, right? So we would talk about brake horsepower in a minute. So volume flow rate is one of the parameters. So it means that how much volume flow rate is going to be achieved by the operation of that pump, right? And then now we need to, and there is another thing which we are interested in, that is net head. That how much head is pressure head, usually that how much pressure head is produced at the pump. So how we can calculate that pressure head? That is usually we say that if this is the pump, yeah, okay, maybe I would draw it like a pump. The operation of the pump is to kind of increase the pressure. So if I say that it is a kind of compression of fluid, so that if this is in and this is out, this is pump. Fluid is coming from here and going out. So if we want to calculate the net head which has been gained by the fluid in the in there, that can be calculated by the head, and we denote it with H net or H simply. So that would be equal to, we can calculate from the Bernoulli's equation, the summation of static plus dynamic plus elevation head at the inlet and outlet. So we, at the outlet it would be P upon rho g, which is P upon gamma, plus V square upon 2g plus Z, which is at outlet, minus P upon rho g plus V square upon 2g plus Z at inlet. Right? So usually the flow through the pump, it has got the same velocity and elevation if we are talking about axial flow pressure. So in that case, it is that head gain in pump is just pressure at a static pressure. So here this is static pressure, static. So that is the pressure we can measure from some gauge, right? P out minus P in divided by rho g, and rho is constant. We are taking it that incompressible fluid. We so rho would be constant at the inlet and outlet, so it would be the same. So we can take it common. So usually these two dynamic heads, they are, and elevation head, they are usually the same at inlet and outlet. So the only main difference is the increase in the static pressure head, right, in case of pumps. So basically we can say that net head is simply the pressure rise across the pump expressed as a head. So it means that it would be in feet or meters, meter of some fluid like mm of Hg or whatever we can. If I can show you that, and there was also a concept of energy grade line. So these three heads make it energy grade line, which you must have studied in hydraulic grade line. In that is only without this dynamic head. Energy grade line, that is the sum of these three head, and there was another thing, hydraulic grade line, which is energy grade line minus b square upon 2d. Right. So I hope that in fluid mechanics 1 you must have heard these three terms. These two terms, energy grade line. So energy grade line for inviscid flow remains the same, horizontal line. So let me show you that what we are talking about here. So energy grade line out minus energy grade line at in. So if I show you that energy grade line basically. So if I show you the figure here, so we have got kind of reciprocating pump here. So if you see here, that energy grade line at the inlet is this line up to here, right? So it means that from this datum point, if we measure the sum of static pressure head plus dynamic pressure head plus elevation pressure head would be equal to this. And because in this, uh, after we go out of the pump, it is increased to this. So it means the difference between this is the energy grade line at the outlet, this is the energy grade line at inlet. So that net head which has been gained in the pump, that is just the difference of energy grade line at outlet minus energy grade line at inlet. And here you can see brake horsepower, which it is the shaft power which we are giving to the fluid. So now let's discuss these parameters which are related with the power which is imparted on the fluid in case of pumps. So now we can, just a minute, let me scroll it. So we first parameter in case of power, that is we call it water horsepower or fluid horsepower. We just call it like horsepower. So horsepower is, it is the useful power delivered to the fluid, and we call it WHP or water horsepower, that is equal to mass flow rate into gravitational constant into H, which is the net head which is gained in that pump, and we can also write it rho into V dot. V dot is the volume flow rate, and G H. And H is here, we can also call it H net. Okay, so this is the useful power which is delivered to the fluid. So if you think that whether this power could be equal to the power which is being applied by the motor, because if you kind of think it, yes. Any question? Anything you want to ask? Any query? Maybe not. Okay. So because there are some kind of rotating component involved, so it means that the shaft power which is coming from that motor, that would be greater than the actual power which is delivered to the fluid, because due to that rotating part there would be some losses inside that shaft and rotor, losses due to friction. So that power which is usually provided by the rotating shaft, that is called brake horsepower. Brake horsepower. We call also called it VHP. So brake horsepower, that is the power which is provided by the rotating shaft or motor. So that would be equal to, as we learned in the last class, that is equal to product of angular velocity omega into torque on that shaft, right? So if we want to see that how much efficient the pump is, then it would be basically the actual useful power divided by the power which is provided by the motor. So if we want to define efficiency of a pump, that would be equal to we call it horsepower divided by brake horsepower. So if we put the formula here, that would be rho g v dot into h net, or we can also write it h divided by w into t sharp. So it is kind of this. You can also take it like that isentropic efficiency thing, right? Which you must have learned in your thermodynamics course. That isentropic efficiency of pump, in which we kind of include the frictional effects in that isentropic efficiency, like 90% or 95%, like isentropic efficiency of pump as well as the isentropic efficiency of turbine. We usually define it in steam power cycle and gas power cycle, right? So I hope that you have got the understanding of that a little bit. So now this efficiency, it has got two extremes. If we look at this, the brake horsepower that is going to be provided by the motor. So if the electricity is there, it is going to provide that. But there are four parameters here, right? So numerator, we have got four parameters. One is rho, which is density of the fluid, which is always greater than 0. G is the gravitational constant, which is again a constant value. The efficiency can have zero value because of these two parameters. One is the volumetric flow rate, or the one is H, which is the net head. So let's discuss these two possibilities. So when we have got volume flow rate is equal to 0, it means that in case of our home pump, it means that we have switched on the motor, but the valve which is installed in front of that pump, which is going to take the water to the overhead tank, we just close it. So it means that the motor is providing the power, but because the valve is closed, it cannot take the water there. So it means that the net head which would be developed, that would be maximum, because the pressure is there, but because the valve is closed, so it means that it cannot travel upwards. So we usually call it a shut off point. So shut off. So we call it shut off point or state. So let me draw it here as well. So if we so let me draw it here. So if this is volume flow rate V dot, and if here we are drawing H, so it means, and efficiency as well. So at this point, if the valve is closed, net head which is available across the pump, that is maximum, right? Because it would have the maximum potential for work, but because there is valve closed in front of it, so efficiency would be zero at this point. So we are talking about this point. Now the second scenario where we would have efficiency zero, that is when h is equal to zero. So it means that it is the point that when h is equal to zero, and we call it free delivery. So it means that there is no kind of impact of that pump. So whatever flow is coming in, it is going at the same head at the outlet. So pump is just flowing, just there, just operating without imparting any useful work on the fluid. So in that case as well, we would have, it means that we would have maximum volume flow rate in that scenario, and in this case head would be zero, net head, because there is no useful work, so we can say that it is going like this. This is head, net head, and we call it H available, right, to do useful work. And for the efficiency, if we plot it, it would look like something like this. It can be higher than, let me, okay, just to make sure that there is no confusion, let me draw it again here. Right. So there would be a point where we would have maximum efficiency. So, so this point, this volume flow rate at which the pump gives us the maximum volume flow rate, that is called best efficiency point. We also call it BEP. Best efficiency point is the point where is the volume flow rate at which the pump gives us the maximum. If the pump is operated at that location, then it would give us the maximum volume, maximum efficiency. But there is also a requirement from the piping system. So that is called, we call it H required. Because pump, like in this figure, there are piping involved, and then there is friction losses here, minor losses, major losses, as we discussed in internal flows. So it means that H required, that is the losses due to friction and different components installed, right? So that we call it H required. So that H required is usually kind of, if I show it with green, so that increases as we increase the flow rate, because we know that if the flow rate is increasing, then we have kind of the losses would increase due to more friction, right, and velocity head. So this is the H required line. H required. Now, if you see that they intersect at this point, so let me draw another vertical line here. So this is the actual operating point of the pump. So whenever we select a pump, it is our kind of desire that this gap between maximum efficiency point and operating point of the pump, it is very close to each other. It it should always be on the right hand side. The operating point should always be on the right hand side, so that the minimum volume flow rate which is required, we are getting it. But we also want maximum efficiency. So it means that we need to kind of select a pump so that we can get the actual operating point near to the best efficiency point. So in that case, the pump would give us the best performance, right? So we will extend this discussion in the next class, which is going to be held. So these are the practical things now we are discussing about the pump selection. So these all these curves, they are being called pump performance curves. And whenever you are in industry, then you need to kind of select a pump depending upon your requirement of flow rate, brake horsepower, and things like that. Then you kind of see the pump performance curve, because these as required depends upon the diameter of the impeller. So if the diameter of the impeller would be changed, it would be different curve. Then you need to decide that what impeller diameter pump I need to select, and what would be the volume flow rate and things like that. So we will take it from here in the next class. So I hope that this introductory class about the pump performance curves are a little bit and different parameters which we discussed, if I can summarize it quickly in a minute: shutoff point, pre-delivery point, then best efficiency point, which is gives us the maximum efficiency, and then the actual operating point, which is where the H available is going to intersect with the H required. H required is the head losses due to friction and different components, which we discussed in the internal flow chapter, which was chapter number 8. So now you can see that all that knowledge is going to be used to calculate H required. H available, we can always get it from the Bernoulli equation, as I shown here at the start, from here, this equation. So then, and the last thing, that we need to make sure that we have got the actual operating point of the pump is on the right hand side, so that the minimum volume flow rate requirement is achieved. So if there is any question, you can ask me now. Otherwise, we will take it from here in the next class. Thank you. So let me